Hello everyone. In this video lecture, I am going to discuss about the effective nucleosors and Slater's rule. This topic is in the first semester chemistry honors and according to FYUGP structure. In this video tutorial classes, I will mainly cover shielding or screening effect, factors affecting the magnitude of shielding effect, effective nucleosors, and Slater's rule. So first of all, I will discuss about the shielding or screening effect. Okay. As you all know that in the center, the nucleus is present. In the nucleus, protons and neutrons are present. As you all know that protons are positively charged and neutrons are neutrally charged. So overall, this nucleus is positively charged. And around this nucleus, this electron, which is negatively charged, they are moving in a circular path, and this circular path are known as orbit. We know that opposite charges attract and same charges repel each other. Since in the nucleus, positive charge is present, so there will be a force of attraction between the nucleus and the negatively charged electron. Similarly, the electron present in the outermost shell, that is in the valence shell, it will also experiences force of attraction from the nucleus. At the same time, this electron which is negatively charged and this one which is negatively charged, so since they are similar in charges, so there will be a force of repulsion among these two electrons. As a result of this force of repulsion, what will happen? The nucleus charge that should be filled by this particular electron from the nucleus, it will be decreasing. So this decreasing nuclear charge due to the presence of inner electron is known as shielding or screening effect. So here definition of shielding or screening effect is given here. The decrease in the attractive force exerted by the nucleus on the valence shell electron due to the presence of inner shell electron is called shielding effect. That means due to the presence of this inner shell electron, the outermost shell electron or outer shell electron will feel less force of attraction from the nucleus. This decreasing force of attraction is known as shielding or screening effect. That means this inner shell electron will act as a shield for the outermost shell electron and nucleus. Now there are several factors on which the magnitude of shielding effect depends. As here we have seen that greater the number of inner shell electron, okay, if number of inner shell electron increases, then there will be more magnitude of shielding or screening effect. That means if inner shell electrons are more, then the shielding effect will be more. This is obvious from this discussion. Next is the type of orbital occupied by the electron. So electron may occupy S orbital, P orbital, D orbital, or F orbital. If that particular electron occupies S orbital, then shielding effect will be more. If that particular electron occupies P orbital, then that shielding effect will be more as compared to D and F orbital. Now, let us see what is effective nuclear charge. Effective nuclear charge is sometimes called as ENC. So due to shielding effect of inner electron, the valence electron will experience less attractive forces from the nucleus, which in turn reduces the nuclear charge. This decreased nuclear charge is called effective nuclear charge. Due to the shielding effect, the nuclear charge that will be filled by this valence electron or outermost shell electron, it will be less as compared to the case when this electron will be vacant. So what will happen? The actual nuclear charge that will be filled by this particular outermost shell electron from the nucleus after neglecting the shielding or screening effect is known as effective nuclear surge. The definition is here. So the effective nuclear surge is represented by the symbol Z star, and this Z is the nuclear surge. That is, the nuclear surge means what? Atomic number for that particular element, and this sigma represents screening constant, which we can calculate from Slater's rule. This particular screening constant is a measure to the extent to which the inner cell electron in an atom are able to screen the nucleus from the chosen electron. That means this particular value, sigma value, will determine how much shielding effect is experienced by the outermost cell electron due to the presence of inner cell electron. Now here we will discuss in detail Slater's rule, which is used for calculating the screening constant, that is sigma. So first, electronic configuration of the element is written in the following order. So 1s, 2s, 2p, 3s, 3p. That means the electronic configuration of the element is grouped like this order. Okay. Suppose if we are going to find out, there are two rules to calculate the effective nuclear surge, or the Slater's rule, which is used to determine the screening constant. In this first rule, it is applicable for electrons present in s and p orbital. Next, we will discuss the rule which is applicable for an electron present in d and f orbital. So if an electron is present in s and p orbital, then the rule will be no contribution for electron in group beyond the one considered. Suppose we are going to find out the effective nuclear surge or screening constant filled by this particular 3p electron. Okay, then for that case we need not to consider the electron present in 3d orbital or 4s orbital or 4p orbital. That means if we are going to find out the effective nuclear surge for this 3p orbital, we need not to consider the electron present in orbital right towards this group, from this group. Then contribution from other electron in the same group, okay, it will be 0.35 and 0.30 for 1s electron. If we consider 1s orbital, then the contribution from 1s orbital will be 0.30. Then contribution from electron present in next inner cell, that is n-1 cell. n-1 cell means what? Suppose we are going to find out the effective nuclear surge or screening constant for this 3p orbital, then this value will be n, and n-1 means what? 3 minus 1, which is 2. So this 2s 2p electron, it represents n-1. So from this electron, contribution will be 0.85. Then contribution from all other electron from inner cell, from beyond this group, from n-1 group, it will be 1. Now let us understand this contribution of electron for screening constant with the help of an example. So suppose we are going to find out the effective nuclear surge for 2p electron in oxygen. So oxygen atomic number is 8. So if we group that electronic configuration of oxygen, then it will be grouped like this: 1s2, 2s2, 2p4. Suppose we are going to find out the effective nuclear surge for 2p orbital, then for calculating the effective nuclear surge for 2p orbital, we need not to consider that particular electron for which we are going to find out the effective nuclear surge. So in this group, all total 4 plus 2, 6 electrons are there, but we need not to consider all the 6 electrons. We have to consider only 5 electrons. That means we will not count that electron for which we are going to find out the effective nuclear surge. So in this group, 5 electrons are there, so contribution will be 0.35. So 5 into 0.35. Then from this particular electron present in this 1s orbital, contribution will be 0.85, and in this group 2 electrons are there. So we have multiplied 0.85 by 2. So shielding constant value will be 3.45. As you all know that atomic number of oxygen is 8. So to calculate the effective nuclear source, that is Z star, we have to subtract this particular screening constant value from atomic number. So it becomes 8 minus 3.45. So it becomes 4.55. That means effective nuclear source held by this 2p electron, it is 4.55. Similarly, if we calculate the effective nuclear source for 4s electron in chromium, then first we have to group that electronic configuration of chromium in this order: 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, then 4s1. So we are going to find out the effective nuclear source for 4s electron. First we will find out the screening constant. So for this particular 4s electron, we are going to find out the screening constant. So since here only one electron is present, as I have already mentioned that for that particular electron for which we are going to find out the screening constant, we need not to count that electron. So contribution from this group, it will be 0. So it becomes 0 into 0.35. Then contribution from, this is n cell, n minus 1, here n value is 4. That means n minus 1 value will be 3. So from the group or from the electron present in n minus 1 cell, n minus 1 cell means what? Electron present in third cell. Total 2 plus 6, 8, 8 plus 5, 13. 13 electrons are there. So from this particular 2 group, contribution will be 0.85. So it becomes 13 into 0.85. Then from rest of the group from in which electrons are present, contribution will be 1. So total 6 plus 2, 8, 8 plus 2, 10. 10 electrons are there. So contribution will be 10 into 1. So screening constant on addition, the screening constant value we have find out 21.05. As you all know that atomic number of chromium is 24. So to find out the effective nuclear source for chromium, we have to subtract this particular screening constant value, which is 21.05, from this atomic number, which is 24 minus 21.05. It will give 2.95. Now, this is the second rule. If suppose electron is present in d or f orbital, or we are going to find out the effective nuclear source filled by d or f orbital electron, then we have to consider this rule. So similarly, the first point is same for both these cases. No contribution for electron in group beyond the 1 considered. That means for the particular group for which we are going to find out the screening constant, we need not to consider the electron present beyond that group. Next rule is contribution from other electron in the same group 0.35. That means for the group in which that particular electron is present, contribution will be 0.35. Then contribution from all other electron lying to the left of D or F group, it will be 1. That means contribution from all other electron present to on the left hand side of that particular group, it will be 1. Suppose we are, in this case, we are going to find out the effective nuclear source for 3d electron in chromium. So we have first grouped this electronic configuration of chromium: 1s2, 2s2, 2p6, 3s2, 3p6, 3d5, 4s1. So we are going to find out the screening constant for this 3d electron. So according to rule number 1, we need not to consider the electron present beyond this group. That means we need not to consider this 4s electron. We will only consider the electron present in this group, then the group present on the left hand side of this particular group. So here 5 electrons are present, so contribution will be 0.35. So similarly, we need not to consider that particular electron for which we are going to find out the effective nuclear source or screening constant. So 3d, here d orbit, in this particular 3d orbital 5 electrons are there, so we have to consider only 4 electrons. So 4 into 0.35, then From the rest of the group, contribution will be 1, and all total 6 plus 2 8, 8 plus 6 14, 14 plus 2 16, 16 plus 2 18. So all total 18 electrons are present in this group. So contribution from this group will be 1, so 18 into 1. So we have got the value of screening constant 19.40. So to calculate the effective nuclear surge, we have to subtract the screening constant value from the atomic number, that is nuclear surge. So 24 minus 19.40. It will give the value for 4.60. Similarly, so now we will discuss some applications of Slater's rule. In our next class, in our next video tutorial class, I will discuss some other examples of examples. That means for other elements, we will calculate the value of effective nuclear surge. Now, in this slide, we will discuss some applications of Slater's rule. As you all know that while filling up electron, we have first filled the electron in 4s orbital, then we will move to 3d orbital. Now this can be explained from the Slater's rule. So potassium. So potassium atomic number is 19. So potassium can have any of these two configurations. 1s2 2s2 2p6, 3s2 3p6, 3d0 4s1. We have numbered this configuration A. Similarly, it can have this configuration 1s2 2s2 2p6, 3s2 3p6, 3d1 4s0. We have numbered this configuration B. Now we will see which configuration will be applicable for potassium. So first we will calculate the effective nuclear surge for configuration A. That means for 4s electron. Now we will see whether that particular last electron will fill up in this 4s orbital or in this 3d orbital. So for that, we will first calculate the effective nuclear surge for 4s orbital. So for 4s orbital, so this 19, that is that value, and that is atomic number of chromium, which is 19 minus. So here 4s electron, we are going to find out the effective nuclear surge for this 4s electron. So contribution from 4s orbital, only one electron is present. So from this particular group, the contribution will be 0. And from the group present on n-1 cell, n minus here n value is 4, n-1 means 3. That means from the electron present in third cell, 6 plus 2, all total 8 electrons are present in third cell. So from contribution from that particular group will be 0.85 into 8 plus then contribution from other group electron, it will be 1, and all total 10 electrons are present, so it will be 10 into 1. So the effective nuclear surge for the configuration 1 is 2.20. Similarly, we have calculated the effective nuclear surge for configuration B. For this case also, here electron is present in 3d orbital, so contribution from this particular 3d orbital, it will be 0. Then the rest from n minus other contribution from other electron left on the left hand side of this particular group, it will be 1. So all total how many electrons are present? 6 plus 2 8, 8 plus 6 14, 14 plus 2 16, 16 plus 2 18. All total 18 electrons are present, and contribution from this 18 electron will be 1. So Z star, that means effective nuclear surge for this 3d electron, it is 1. So we have seen that effective nuclear surge of 4s orbital is higher as compared to 3d orbital. So this configuration will be applicable for potassium. So while writing the electronic configuration of potassium, always we write down this configuration, as the effective nuclear surge for 4s orbital is higher as compared to 3d orbital. So this configuration will be applicable. Next, we will see why 4s electrons are removed before 3d orbital in the conversion of transition metal to cation. So for the d block element or for the transition metal, so while converting them to their cation, always the electrons are removed from 4s orbital, not from 3d orbital. So now we will see why electrons are removed from 4s orbital, not from 3d orbital. So here we have write down the electronic configuration of chromium. So here We have proved that electronic configuration 1s2, 2s2 2p6, 3s2 3p6, 3d5, 4s1. So first, for 4s electron, we will find out the effective nuclear surge. So first we will calculate the screening constant. So 4s electron contribution will be 0.35. Since only one electron is present here, so from this particular group, contribution will be 0. Then from the electron present in n-1 cell, so here n value is 4, principal quantum number value is 4, that means n-1 means 3. That means for the electron present in third cell, contribution will be 0.85. So all total 6 plus 2 8, 8 plus 5 13. 13 electrons are present in n-1 cell, that means in third cell. So contribution will be 0.85. All total 13 electrons are there, so we have multiplied 0.85 by 13. Then contribution from other electron present on the left hand side of this n-1 cell, it will be 1. So all total 10 electrons are present here, so contribution will be 10 into 1. So screening constant value we have find out 21.05. Now we will calculate the effective nuclear surge for this 4s electron. So effective nuclear surge for this 4s electron is found to be 24, that is atomic number of chromium, minus 21.05, screening constant. So we have got 2.95. Similarly, now we will calculate the Z-star effective nuclear surge for 3d electron. So to calculate the effective nuclear surge for 3d electron, we need not to consider this electron, 4s electron. This is because this 4s electron is present beyond this or on the right hand side of this particular group. So for 3d, if we consider the if we are going to find out the effective nuclear surge, so total 5 electrons are there, so we will only consider 4 electron. Okay, so 4 into 0.35 plus from the rest of the electron present in other group, contribution will be 1. So all total 6 plus 2 8, 8 plus 6 14, 14 plus 2 16, 16 plus 2 18, 18 electrons are there, so contribution will be 18 into 1. So we have got the screening constant value 19.40. So to find out the effective nuclear surge, we have to subtract the screening constant value from the atomic number, that is 24 minus 19.40, we have find out 4.60. That means effective nuclear surge failed by for this particular 3d electron, it is 4.60, and effective nuclear surge failed by this 4s electron, it is 2.95. As the effective nuclear surge for 4s orbital is higher, not 4s orbital, 3d orbital is higher, so while converting the metal into its cation, electron will be removed from 4s orbital, not from 3d orbital. Similarly, we can explain order for successive ionization potential. We can also explain why cation is smaller in size than its parent atom, and we can also explain why an anion is bigger in size than its parent atom. In our next video tutorial classes, I will explain all these three phenomena. I will also try to find out, I will also show some examples of other elements. And thank you. We will again see in our next video tutorial classes.